City College has a space simulator.
We know. Close the door.
As I was saying, on Monday,
City College will be unveiling the City College
Cosmic Pioneer, their very own orbital launch simulator. Pretty soon, they will have an astronaut on their brochure, and we will still be bragging about our foosball table.
Well, what can we do?
We can launch our own space simulator. Before they simulate their launch on Monday, we simulate a launch this weekend. We make Greendale, not City College, the first community college to pretend to put a man in space.
Do we even have a simulator?
We can get one. I admit, it could use a good wash. And I've got just the crew to wash it.
Can we stop walking in slow-mo now?
20 more yards.
You guys are walking in slow-mo?
Give me some more time in a dream. Give me the hope to run out of steam. Somebody said it could be here. We could be roped up, tied up, dead in a year. Oh, I love you more than words can say. I can't count the reasons I should stay. One by one, they all just fade away. Oh, I love you more than words can say.
Hello and welcome to Astronomy on Tap number 68. I am going to be singing that song in my head for the entire show. If you have not watched Community, please do so. It's so good. Hi, I am Rebecca Larson. I am a PhD student here at the University of Texas in Austin, and I am your host tonight. My co-host is Dr. Michaela Bagley.
Hello, I'm a postdoc at the University of Texas at Austin. I study galaxies in the distant universe with Rebecca.
So without further ado, let me share our opening and we can get started. So like I said, that's us. I guess I should put that up beforehand. Whatever. All right, so tonight we have our special undergraduate edition of our show. It is May and it is graduation time, and it is a good time to start to think about what our undergraduate students have done during their time as undergraduates, are doing now, and we wanted to showcase some of the amazing scientists that we have early on in their career and some of the work that they did while they were still taking so many classes as undergraduates. So we have three great talks tonight. First up, we have Zoe De Beurs, who is going to tell us about AstroAI, or how machine learning can help us understand the universe.
Next up, we have Isaac Laseter, who will be telling us about magnifying early Milky Ways.
And last but certainly not least, we have Dustin Katzberg, who's going to be telling us about outbursting white dwarf stars and the homogeneity of binary star systems.
Science is better with beer or wine or juice or water or whatever you happen to have with you tonight. Enjoy the show on your couch, on your bed. As we all socially distance, we are still excited to be talking about astronomy with you all. We would like to take this time to thank the North Door, our sponsors. They are really struggling in this time while we're all trying to be safe and stay indoors and stay away from crowded places. Our hearts go out to the North Door for all they have done to give us an incredible venue and just a really great place to run this show. We hope to be back with them soon.
Another shout out to the Austin Astronomical Society for being amazing sponsors of our show. We give a shout out to them. They're normally in the front row every time we're live in the venue, but I know they're all here now. So everyone say hello in the chat. Everyone else, also please in the chat, let us know where you're tuning in from. We'd love to hear where everyone is watching the show from, since normally we're just a local Austin situation. It's now really cool to be able to get viewers from all over the place. I also want to give a shout out to Odell Brewing Company. They're our other sponsor. I actually am drinking Odell beer this time because I found it at the store. I'm very excited. But before we begin, we also want to reiterate our thanks to the North Door, our normal venue where we host the show, and we've hosted the show in the past 5 years, every single month at that location. The North Door can really use our help. The staff that work there have lost their revenue due to the shutdown and the quarantine. And so if you would like to help out during this time, please go to this link. There's a QR code on the screen. The link is also going to be put in the chat by our amazing helpers and all the rest of our team who's not actively on video. And we also would just love for you to help us help them in this time until we can get back to being in person. The link will be there. Help us get them the support that they really need.
During the show and after the show, connect with us on social media. We are on Facebook, Twitter, Instagram. We also have a YouTube channel, which you have clearly found. But you can check out on this channel other videos from past shows. There's a small gap in the shows that we are still getting up on the YouTube channel, but for the most part, they're all there dating back to the very beginning. So there's plenty of awesome astronomy to go back for as you're bored in between shows. And yeah, check us out on Facebook and Twitter. We post a bit about these shows, and we're starting to add some more content as we all hang out at home.
Also, you can please interact with us during the show. So even while we're trying to do this all virtually, we would love to have you ask questions in the YouTube comments. So if you're watching the video in the chat, you can go ahead and drop any questions. Please do so as they come to you during the talks. And then at the end, we'll ask our speakers those questions. If you also have Twitter, you can ask those questions over there using the hashtag AoTATX number 68. And then you can also please tag us at AoTATX. If you have other kinds of social medias, we will do our best to keep an eye on them during the show. But these are the two easiest ways, the YouTube and the Twitter, to send us questions that you might have for our speakers.
And just again, a quick shout out to all of the awesome space cadets who are behind the scenes, manning all of this, taking care of getting all the questions and posting links and everything. So shout out to everybody who you don't see on screen, but is still super necessary to make this show happen. And as this—
Absolutely, it takes a whole team.
A big one. So as this says, we are doing trivia. That is this time a correct link to the trivia game. Please click on it, play it during the show. It will be open for a while after the show, so you can play it at your leisure. It is exciting to have all three of our speakers contributing to our trivia questions. Listen to their talks because they will answer the questions during their talks. So pay attention there, and they'll help you get those answers right. Just a reminder that you do not have to get a perfect score or even get the highest score to win a prize. We do choose a random winner, so play just to play, and we have some awesome prizes that we will drop off to your door if you are local in Austin, or mail to you eventually once we get that happening.
We ordered boxes to ship things in, and they arrived. So now we have a container to convey your prizes to you. And we just have to figure out how to do the postage part. So we're getting closer to being able to get you trivia prizes. Sorry. I don't remember if I made a slide about this. I did not, but there is another link to a survey. So we also put together a survey for you to fill out if you have gone to our shows before, or if you have not gone to our shows and you've just been watching us on the internet. We're trying to figure out other ways that we can connect with you online, virtually, and especially during this time in quarantine. We have the link in the description of our YouTube video, and our wonderful team is also putting those links into the chat for you as well. If you could fill out that survey and give us an idea of any of the other things that you would like to see us try to do during quarantine, or doing it virtually, adding things to our YouTube, doing a website, online store, and things like that. There's questions about all of those on the survey, or if there's just something that you would like to see that you haven't seen from us recently or at all, please let us know.
please be kind to each other during this show and at all times when this is a pretty stressful time for everybody. But specifically right now, please be respectful with your comments and your questions in the YouTube channel, on Twitter, be patient with any technological issues we might have. We're all, we've done this a few times, but we're still kind of making it up as we go. And again, we have people who are perusing all of the YouTube comments and will find your questions, and we will try to get to them. So please be patient and respectful to everybody involved in this show.
All right, so without further ado, let's get started. All right, so if we could have Zoe please show up on your video here. Awesome. Turn your video on, Zoe. Perfect. So Zoe is an undergraduate researcher at the University of Texas at Austin. She'll receive her bachelor's in physics and astronomy honors in May of 2021 and has done research internships already at the University of Chicago and Harvard-Smithsonian Center for Astrophysics. Zoe studies how artificial intelligence can help us understand exoplanets, black holes, and neutron stars. Ultimately, she hopes to become a professor where she will not only uncover the mysteries of the universe through her research, but also inspire and mentor the next generation of scientists, especially those from underrepresented groups. So Zoe, please take it away.
Awesome. Thank you so much for that introduction, Rebecca. Yes, so as Rebecca said, my name is Zoe De Beurs, and I'm a fourth year physics and astronomy student at UT. And in the past 4 years, I've had the opportunity to do research projects at UT and beyond. And today I'll be talking about how machine learning can help us understand the universe. So first off, what is artificial intelligence not? So artificial intelligence is not the Terminator, it's not the Matrix, and it is not RoboCop. Those are not necessarily examples of what we're talking about in astronomy when we say artificial intelligence. Although these movies are obviously very entertaining and futuristic, that's not really what we mean. These movies portray some machine learning methods. These movies portray some of the common myths about artificial intelligence. So one of the common myths that we see is that people think that artificial intelligence works the same way as our human brains do. And although some machine learning methods are kind of modeled loosely after the structure of our brains, they're not the same. In the end, machine learning is a form of computer engineering that is getting better and better at tasks that it used to be that only our brains could do. But sometimes artificial intelligence can also fail at tasks that our human brains can do really easily. So they're not the same thing. Another common myth is that artificial intelligence can be 100% objective and is free of all human biases. Unfortunately, that is also not true. Machines can actually be just as biased as the humans that built them. And this is actually one of the big challenges in the field. So the third myth that people often think about artificial intelligence is that they think it will replace more jobs than it actually creates. But according to several studies, AI will obviously replace some jobs and automate some of them, but it will actually create way more jobs than it will actually take away. So we talked a little bit about all the things that artificial intelligence is not, but what is it instead? So, I said these movies are not necessarily examples of artificial intelligence, but artificial intelligence instead is a set of different computer systems that can do tasks that normally would require human intelligence. And you may have heard the terms artificial intelligence and machine learning kind of used interchangeably as if they're the same thing. But machine learning is actually a subset and kind of an application of artificial intelligence. So artificial intelligence is like kind of the umbrella term, and machine learning are like some examples of this. And machine learning allows these systems or things to kind of automatically learn and improve from experiences and learn from examples without me as the computer programmer explicitly saying, do it this way or do it that way. But instead I give it a bunch of examples, a bunch of data, and I ask it to learn from that data. So what would be some examples of this and what does it actually look like? So here we have an example where we have thousands of images of cats and thousands of images of dogs. and we want to use a certain machine learning method called a neural network. And what this does is it feeds all of these images into the structure that's kind of similar to the neurons in our brain, but also somewhat different. And it tries to learn kind of all the different features from these images. So it might learn something about that there's more contrast in dogs than cats, or certain shapes are different, or things like that. And it kind of iterates and goes through this process several times until it gets better and better at predicting that this is a cat and not a dog. But beyond cats and dogs, machine learning can be really powerful in other ways, and you've probably encountered it in many things in your daily life. So some examples are virtual personal assistants. So maybe you have Alexa at home, or you have Siri on your iPhone. These are examples of things that actually use machine learning to be able to do this. Other examples are Google Maps, or fraud detection with banking, or recommendations from Spotify are also based on using machine learning algorithms. And another really important example would be for medical diagnosis. So people might use medical images and can actually figure out whether someone might have lung cancer or might have something else instead. But beyond all of these applications outside of astronomy, today we want to talk about what machine learning and artificial intelligence can help us learn about the universe. So there are a lot of different ways that astronomers can use artificial intelligence to understand the universe. But today I'll be talking about two primary questions. And these have been questions that I've kind of sought to answer in my own research and find really interesting. And I hope you guys do too. So the first question is, how are black hole systems distributed all over the universe? And what can machine learning teach us about how galaxies form and evolve? The second question we'll be answering today is whether exoplanets, so planets that are outside of our solar system, whether those planets are anything like planets inside of our solar system. And can we use artificial intelligence to find smaller and smaller planets that might be similar to our Earth? So let's start with the first question. So these black hole systems are sometimes referred to as X-ray binaries. And this is for two reasons. So these systems can consist of something that's really, really massive and really dense, which can be a black hole, but it can also be something else sometimes. And together with that, it has a second thing attached to it called a companion star, or you can think of it as kind of like a buddy. And together they move around each other. And as that is happening, they release a bunch of energy in the form of X-rays, the same way that you might get X-rays when you're trying to get like a chest X-ray. And so they're called X-ray binaries because it's two things, so a binary, and they release a bunch of X-rays. And so to kind of give you an intuitive understanding of what that actually looks like, I'm going to play this little video that was made by an artist. And you can see some of the arrows might be a little bit incorrect, but you can see that you have this really massive dense thing that could be a black hole together with this other object, and they're orbiting each other. And as that's happening, it's sucking a bunch of matter into this really hot gas until eventually all of this stuff from this other star disappears into the black hole. So I mentioned that that really massive thing can either be a black hole or it can be a black hole imposter, as I like to call it. And so it can also be something called a neutron star or a non-pulsing neutron star. And essentially that's something that's also a really old star, which is also really small and dense, just like a black hole is, but light can actually escape it. And it's been a really long-standing question for astronomers to be able to actually look at these systems and be able to say, does it actually contain a black hole, or does it maybe contain one of these black hole imposters? And even though we've seen thousands and thousands of these systems, we've only been able to say for about 30 of them, that's definitely a black hole and not one of those black hole imposters. So this is something that we try to tackle using machine learning. But before I go into that, I want to give a little bit of context of how someone might have solved a problem like this more than 100 years ago. So more than 100 years ago, before modern devices such as laptops and mobile phones were invented, a computer was actually a person who did calculations. So at the Harvard College Observatory, between the late 19th century and early 20th century, there were more than a dozen women who were computers, and they laid out some of the most fundamental assumptions that we know about astronomy today. But they didn't do this in the same way that we do now. What they did is they looked at these photographic plates of the night sky, and they would look at how the positions of stars would change over time. And the reason they were hired is partially because as the business of astrophotography grew, there were so many plates that there were not enough people to actually look at these images. And so the director of the Harvard Observatory at the time hired women to analyze these images, and they made some really groundbreaking discoveries. And it's really interesting because it's kind of analogous to some of the problems astronomers are having today, where we have such huge amounts of data where the number of eyes or the number of astronomers are really not enough to analyze all of it. However, nowadays, we're using a very different kind of computers to solve this. Instead, we're using machine learning algorithms to make discoveries about the universe. So what does this actually look like? So astronomy has changed quite a bit since the 1870s, and most observational astronomers will often have a workflow kind of similar to this one. So we might have data coming from a telescope. So this is coming from the Monitor of All Sky X-ray Image, or MAXI, which is aboard the International Space Station and was one of the first missions to be aboard the International Space Station. So we have our data coming from there. Then we use something like Python or some form of code to actually extract that data. And then we might collaborate with other scientists. So this is a picture of me actually also at Harvard last summer working with a bunch of other students. And then we use some other software to actually plot our data and analyze it. And we can do this all from the comfort of our own desks. But let's go back to the original question of what we were trying to solve and what methods we're using to do that. So we're talking about black hole or black hole imposter. What are we seeing in these X-ray binary systems? So I mentioned that thousands of them have been detected, but for only about 30 of them do we know that these definitely have black holes in them and not these imposters. And this is because the current methods that people use are limited to really bright objects, and they can require a lot of observations and having to follow up several times. And so as we enter kind of this big data era, it becomes really important that we have a really simple, efficient, and reliable method of being able to say whether they're black holes or black hole imposters. So last summer, I wanted to look at 3 different commonly used machine learning methods: a Bayesian-Gaussian process, k-nearest neighbors, and support vector machines. And these are really widely used by people in the machine learning community. I'm going to explain one of them, called k-nearest neighbors, and this is one of the most widely used, but also one of the easiest to understand and one of the most efficient algorithms. So if we took a really simple example and we had a bunch of black holes and a bunch of these black hole imposters called neutron stars, and we have 2 different dimensions that they occupy, then let's say that we have this example right here where we don't know, is this a black hole or is this a black hole imposter? And let's say that we want to look only at the 5 nearest neighbors. So we say k is equal to 5. Then what it will do, the algorithm will calculate the distance to every single point first, and then it'll figure out what are the 5 closest ones. So if I have 5 over here, it'll see that 3 out of 5 are these black hole imposters called neutron stars, and 2 out of 5 are black holes. And then it'll just go by a majority rule. So it'll say this is a black hole imposter because 3 out of 5 are neutron stars and 2 out of 5 are black holes. So it's a very simple algorithm with a really clear-cut way of making a decision as to what this unknown object should be. So how does this actually do on the data that we were looking at? So we found that for our data set, about 92% of our different kinds of sources were correctly classified. So 88% of our black holes were correctly classified, and the other black hole imposters also had a pretty high accuracy rate, which is really exciting. But you might wonder, okay, that's cool, but what does that actually tell us about the universe, and how does that help us understand the universe? So this is really important because we've known that really high mass, so really massive X-ray binaries, they often trace regions of star formation, whereas the lower mass ones kind of trace the way that the mass of stars is distributed throughout a galaxy. And so this can tell us a lot about how galaxies form and evolve. And so if we can increase our understanding of these black hole imposters or real black holes in these X-ray binaries, that can help us understand galaxy formation and evolution in the universe. Okay, so we answered our first question, that indeed this machine learning method of using k-nearest neighbors and some of the other ones can teach us about how galaxies form and tell us more about how these black hole systems are distributed throughout the universe. So let's move on to our second question. Are exoplanets, so planets outside of our solar system, anything like planets inside of our solar system? And can we use artificial intelligence to find smaller and smaller planets? So the mystery of possible other worlds have fascinated star watchers since Copernicus's time. And astronomers have sought to discover Earth analog planets outside of our solar system since the 1940s. However, until about 30 years ago, we saw no signals of planets outside of our solar system. But now we are observing smaller and smaller planets as we become more sensitive and we develop all these new techniques of being able to actually find these planets. So how many planets do we actually know of now? So this is an animation that shows you some of the planets that were discovered by planet hunting mission Kepler. And this is only a slice of all the planets that have been found so far. So as of last week, there were about 4,154 planets confirmed. And you might wonder, well, are these planets anything like planets like our Earth? So that's still a big question in the field. We still want to really find more planets that are smaller and smaller in size, that are more like our Earth. And that's been something that's been really challenging. So you might wonder, okay, well, how do you actually find all of these planets? What do you do? So one of the primary methods is called the radial velocity method. And how it works is if you have your star over here and you have a planet going around it, when that happens, the star actually also moves a little bit as they're like pulling and tugging onto each other. And so we can actually measure that that star is moving. And this is called a stellar wobble, if you've heard of that before. And so how do we actually measure this? So we can look at the spectrum of the star, so all the different colors that are coming off of it, and we can see that as the star is moving away from us, it'll become more red. And as it's moving towards us, it can become more blue. And so this is the average spectrum, and we can look at how that is shifting to the left and the right. And that is how we can see whether our sun might be moving because of a planet being tugging onto it. However, this is unfortunately not perfect. And that's because stars have these dark spots onto them called sunspots. And these sunspots can also cause a shift in that average spectrum and can change the shape. And that shape change is much bigger than the shape change that you would see from Earth mass exoplanets. So for example, this might cause a shape change of about 5 meters per second in magnitude, whereas if you wanted to look at an Earth mass exoplanet, it might only be about 10 centimeters per second in magnitude. So our solution is to train something called a neural network to remove that noise from those sunspots or from this stellar activity. Before I go into what a neural network is, let's go back to our drawing board of what all these different things are. So we talked about artificial intelligence as the umbrella term, and then we talked about machine learning as being a system of ways to apply some of these methods. And then the last thing that we should talk about is something called deep learning, which is the learning of underlying features or certain properties in data using deep neural networks. So that's what we're using in this specific method. So this neural network will take in that average spectrum that we were looking at earlier, and we'll put it into one of the first layers of the neural network, and then it'll try to figure out what are all these features, what are the features in shape, and what might allow us to actually predict what that noise is from stellar activity. And it'll do this for a whole bunch of examples until we can get closer and closer to removing as much of that noise as possible. So to be able to do this, we are using data from the HARPS North Solar Telescope, which is a high precision spectrograph, which just means it's really precise at being able to measure that spectra that we saw shifting to the left and to the right. And it's able to detect really small changes in that. So the HARPS North Solar Telescope is located on the Canary Islands in Spain, and we had observations from it from July 2015 until December. And here are some nice pictures of the telescope as well. So when we actually use the data from this telescope and feed that into a neural network and try to figure out whether we can remove that noise, how well does it actually do? So we found that with the data from the HARPS North Solar Telescope, we can actually successfully remove noise from the data. So we start off with a raw amount of noise or scatter of about 1.37 meters per second, which means that we would normally be able to detect a planet that is about 15 times as massive as the Earth, and it would be some kind of a gas giant like our own, like Neptune in our own solar system. But when we actually feed it into this neural network, we can correct this and get rid of a lot of the noise and get to about 0.85 meters per second. And that means we would be able to detect a planet of the size 9.3 times the mass of the Earth, which would be a really large rocky planet. And so this is a pretty big deal. And what does that actually tell us about the universe? So we found that when we can remove this noise from these dark spots, we can become sensitive to smaller and smaller planets. We can increase our understanding of planets outside of our solar system, and we can find smaller planets that might be more and more similar to Earth-like planets. So in conclusion, we found through all these different things that we talked about that machine learning is a powerful tool that can help us distinguish black holes from black hole imposters. We can classify black holes and thus map kind of where all these X-ray binaries might be located, and we can use machine learning to help us understand galaxy formation and evolution in the universe. Secondly, we found that deep learning methods can remove noise from these stars that are beyond our own solar system. By removing this noise, we can also use deep learning to become more and more sensitive to smaller and smaller planets that are more similar to our Earth. And overall, we found that artificial intelligence can help us understand some of the most curious and critical celestial objects in the universe. And with that, I would like to thank my advisors for all their help and belief in me. I would not have been able to do all of this really exciting work if it wasn't for all of their support and just constantly believing that I can do something even if I'm struggling a little bit. So I really appreciate that. Thank you. Thank you for listening.
Awesome. Thank you so much, Zoe, for that incredible talk. You covered an unbelievable amount of material there, and that was an awesome talk. Thank you. We have a few questions that we're going to ask Zoe now, and then if we don't get to your question now, we might stick around and do sort of like a panel discussion at the end. So hang tight if you can. But Zoe, the first question we have from Alan is, what's an example of a task that AI can't do but humans can?
Yes, that's a great question. So some examples of this would be when we look at, you might have had this as well when you use Google Translate, for example, that even though we can get really close to something that's similar or like almost correct in another language, it's not perfect at it. And some really basic grammar things that we as humans think are super obvious and intuitive, AI sometimes still fails to be able to grasp. So that's one example. I think that those are some of the primary ones, but I think another like kind of big picture thing to keep in mind is that usually AI cannot learn more than you kind of provide it. So if you give it a bunch of data, it'll kind of learn exactly what's in that data. But if you suddenly give it a bunch of other data that has very different information, it might not be able to learn from that if you didn't kind of train it on that. So it is really important that whatever you put into it, you will get out of it, if that makes sense.
Okay, yeah, so it really matters what you teach it, what it learns.
Yeah. Yes.
Okay, that sort of feeds into our next question, actually. So Lisa asks, and this is my mom. Hi, Mom. Lisa asks, can AI programs learn about black holes or exoplanets without being directed by humans? And does its thinking evolve?
Okay, so maybe in the future, we would be able to kind of let artificial intelligence run loose a little bit more. But as of right now, you really do have to kind of show like, here's the kind of input of all the information I give you. Here's the answer. You kind of try to figure out what's in between. There are some AI methods that don't necessarily always give the answer and ask it to kind of learn something completely new without you telling it exactly what the answer is. But the methods I kind of talked about today all kind of give already an answer, and the machine learning method learns based off of that. And if you gave it like an example that it has never seen before, sometimes it really doesn't know what to do at all. So I think that that's like a good distinction too. Like us as humans can sometimes be really good at extracting or like figuring out something new without really having seen it before, whereas a lot of machine learning methods fail at that.
Okay, interesting. Okay, so right, so they won't be necessarily great at finding like the weird, funky objects or new discovery type spaces.
Yes, it depends. Like so it's not that it can't find something new, but if it's really different than anything you've ever seen before, it might be very difficult for one of these models to be able to detect that. It might be able to detect that it doesn't know what it is. That's possible. Like if it's like not sure what it is, but it might not be able to say what it is instead. Cool.
Okay, awesome. And so that also kind of segues into our next question. This one's a little bit of a doozy. I'll read it all, but I think, it's cool. Okay, so Charlie asks, how would you approach initially seeding an AI or machine learning data set for something as massive as the universe? It just seems so infinitely data intensive. Would you focus on small goals first and then expand? Do you keep the parameters purposefully narrow? So sort of like I guess, how do you simulate a whole universe? Or do you have to break it up into smaller chunks to make it more manageable or limit some of the parameter space that you explore?
Yes, that's a great question. I think that, so even though it would be really cool if we could just give some kind of machine learning model all the data and just ask it to figure out what to do next, that is really hard to do. Instead, we often kind of try to break it up into smaller problems, kind of like the person who asked the question implied, and try to solve those first. And then we can kind of start asking more complicated questions as we go on. Kind of the same way that you might in school kind of like teach a kid some simpler things, like how to write letters, and then maybe eventually you form sentences and kind of increase complexity as you go. It's kind of the same thing with a lot of these methods.
Nice, that was a great answer. Okay, thank you so much, Zoe. If you don't mind sticking around, we will have some more questions for you at the end of the show. But for now, please turn your video off, and I'm going to ask Isaac to come join us here. So Isaac, if you're around, awesome. Can you turn your video on so everyone can say hi? Okay, awesome. So Isaac is an undergraduate researcher at the University of Texas at Austin. He's majoring in astronomy and physics. He will be graduating this semester, or I guess like officially graduating on Sunday, I think, right?
Yes.
Awesome, good, exciting, congratulations. And he's excited to start his doctorate program in astrophysics this fall at the University of Wisconsin-Madison. When he's not studying or doing research, you can find him either in the gym, skydiving, or hiking. So Isaac, please share your screen and take it away.
Awesome. Okay. Hopefully everything is working and everyone can see my slides. Good evening. As Michaela said, my name is Isaac Laseter, and I'm currently, but not for long, an undergraduate at the University of Texas at Austin. Commencement is a week away, so I just made the cutoff for this presentation. School's not over though for me, as I'll be starting my PhD program at the University of Wisconsin this fall. Now, the title of this presentation was Magnifying Early Milky Ways, which is extraordinarily more catchy than the real title of the research, which is Utilizing Gravitational Lensing to Discover Lyman alpha emission galaxies. And I hope I didn't already bore anyone 30 seconds into my presentation, but I promise it's exciting and that you will all be experts by the end. Just to put some perspective into the project, when I say galaxies, the majority of you will think of an image like Andromeda, or maybe this artist's rendition of our Milky Way. But the galaxies I'm interested in look more like this. And I'm sure no one will be making this galaxy their desktop background anytime soon, but that's entirely okay. I understand. These blobs, however, are really the galaxies you see to your left, Andromeda, Milky Way, but billions and billions of light years away and in their adolescent phase. It's precisely in studying in great detail these early Milky Ways where we can get tremendous insight into a more complete picture of galaxy evolution. Now, there's a lot to unravel, and I don't want to take up too much of your time, but I want to work my way through that boring title so that everyone can understand what I've been working on. Now, the first few words of the title are utilizing gravitational lensing. But what is gravitational lensing and why am I utilizing it? Now, I'm sure a lot of you have glasses, and I'm not talking about glasses like this with alcohol, but eyeglasses. Why are your eyeglasses important? You would probably answer that they improve your eyesight or enhance the clarity of what you see. Gravitational lensing is the same in the sense that it not only enhances what we see, but it allows us to see things we couldn't have without it. And it accomplishes this by the bending of space and therefore light. Many of you may know that any amount of mass distorts space and time. However, when you have an exceptionally massive object, it distorts space and time to such an extreme amount that we actually see that distortion. So much so, if a galaxy is hidden behind another supermassive galaxy, we can actually observe that far galaxy since that massive galaxy is distorting space so much. And you can really see this distortion in the animation to the right, which is a simulated black hole passing in front of a galaxy, showing that distortion. And the animation to the left is actually showing how galaxy clusters distort space to the point where we can see a background galaxy. Now, I'm sure if you're watching Astronomy on Tap, you've probably seen the movie Interstellar before, starring UT's own Matthew McConaughey. You can actually see gravitational lensing in that movie if you pay attention to the wormhole or the black hole. Now, instead of distortion from a small wormhole next to Saturn or wherever it was, I'm looking at the distortion caused by entire galaxies. Now, instead of just speaking about a galaxy with an arbitrary distance from us, I want to quantify that distance. And to do that, I need to introduce another concept, which actually isn't in the title, but is extremely important in the majority of astrophysics. And that is redshift. Now, all of you, and I mean all of you, have experienced redshift before. You've been driving, and because everyone here are excellent drivers, you hear an ambulance or a police car coming, and you pull off to the side. And you notice that as the emergency vehicle makes its way towards you, the pitch of the siren increases. When the vehicle passes you, the pitch decreases. What's happening is the sound waves from the siren are occurring more often, or its frequency is increasing while the vehicle is approaching you. And when the vehicle is moving away, the crest of the sound waves are occurring less frequently, thus making the pitch decrease. Now, this is called the Doppler effect, but it is the same exact thing as redshift, except with the vehicle, with the siren, it's sound, it's pressure waves. Redshift, in an astronomical sense, is light. So a galaxy moving towards us has an increase in its light frequency, making it appear more blue or blue shifted. Whereas a galaxy moving away from us has a decrease in its light frequency, making it appear more red or red shifted. Now, redshift has a few quirks to it that I want to highlight. The first is that redshift is just a number. It's not meters, it's not seconds, it's not inches, it's not miles per hour, it's redshift. So you can actually interpret redshift in slightly different ways, and they are correct. The way I typically think about redshift is the thought of redshift as a time after the Big Bang. But you can also think of redshift as a distance from us. With the table I've included, you can see how redshift corresponds to both a time and a distance. But a closer look at the table highlights another quirk of redshift. And that is a lower redshift is a further time after the Big Bang and a closer distance to us. So a redshift of 0 is right here, right now, 0 inches away and 13.7 billion years after the Big Bang. And so a high redshift of like 3 is tens of billions of light years away and is only a couple billion years after the Big Bang. Now, many of you might be saying, but he said a high redshift. 3 is relatively not a high number, and astronomy prides itself on having the largest numbers. But 3 is indeed high. And that sort of shows the last quirk. And that's that redshift does not scale in a linear fashion, meaning a redshift of 0 to 1 is different from a redshift of 1 to 2. With a redshift from 0 to a redshift of 0.5, we've already covered 6 billion light years. Now, looking at the universe as it was 5 billion years ago. So, to bring back gravitational lensing, in my research, the forefront massive galaxies, the ones that are doing the lensing, the ones that are distorting space, are around a redshift of 0.5. And the lensed galaxies, the ones I'm interested in, are around a redshift of 3. So I'm using a galaxy that we see 8 billion years after the Big Bang to study a galaxy that we see only 2 billion years after the Big Bang. Or you can think I'm using a galaxy 6 billion light years away to study a galaxy that's 19 billion light years away. But when I say galaxies, these aren't just any old galaxies I'm interested in. These galaxies are Lyman alpha emitters. And this brings us to the next part of the title. Now, Lyman alpha is just a photon with a specific wavelength or frequency emitted from a hydrogen atom. It's just light with a specific wavelength that comes from hydrogen. I won't get into the trenches about the emission mechanisms of this light. But if you're curious, I would love to answer that question after. So Lyman alpha emitters are just galaxies that are emitting Lyman alpha. But what makes them important is that these galaxies have very specific characteristics about them. They are typically very young galaxies that are only a few hundred million years old. And they also form stars more than any other galaxy. And we know this because Lyman alpha's rest wavelength, the wavelength at redshift 0, what we measure in labs on Earth, falls under UV light. And the most common sources of this realm of energy of UV light are O and B stars, the very massive, blue, short-lived stars that emit the majority of their light in the UV. And it's because these stars are so short-lived, we know the galaxies are very young and have a very high star formation rate. And it's because of their youth and their star formation rate that Lyman alpha emitters are showing us what Milky Way type galaxies looked like early on in their life. We're looking at the Milky Way's baby pictures. And I want to study those baby pictures in great detail. And now I can bring everything together. Lyman alpha emitters are immensely important in understanding galaxy evolution. But because the Lyman alpha emitters that we want to study are at such a high redshift, meaning they are tens of billions of light years away, it's hard to study them in great detail. So to increase that detail, I'm looking for Lyman alpha emitters that have been gravitationally lensed. And so to actually dive in now, many of you might be wondering how I know that a photon is a Lyman alpha photon. How do I know when I look at a galaxy that it is a Lyman alpha emitter? After all, the pictures I showed contain much more than one particle of light, and they all look identical. Well, I'm actually not interested in their pictures. If I was a detective, I'm not interested in the mugshots of Lyman alpha emitters. I'm interested in their fingerprints. But what is a galaxy's fingerprint? Well, their fingerprint is their light spectrum. This image is showing what type and amount of light we are getting from a galaxy. Specifically, this image is NGC 2276, which is a spiral galaxy about 100 million light years away. It's just an example. What's important, though, is that the peaks of the spectra correspond to a flux, or the amount of light we are receiving. And its location on the x-axis tells us its wavelength, or frequency. So we can look at the spectra and pinpoint specific light. Because Lyman alpha, remember, is just a photon with a specific wavelength from hydrogen. Photons come from oxygen, carbon, any other element you can think of, all with their own specific wavelength. So looking at a galaxy's spectra, we can point to what type of light that galaxy is emitting. So now it's simple. To find Lyman alpha emitters, I just need to look at high redshift galaxies until I find Lyman alpha in the spectra. But that's not enough. Remember, I'm not just looking at one galaxy. I have a massive galaxy in the way that is doing the lensing that allows me to see what galaxy I'm interested in. I have two fingerprints, two spectras on top of one another. And so to overcome this problem, I chose fingerprints, the spectra, that are not supposed to contain Lyman alpha whatsoever. I'll say that one more time. I chose fingerprints and spectra that are not supposed to contain Lyman alpha. And I can do this choosing based on what we know about Lyman alpha emitters. Remember, they are young and have incredible star formation. So I can look at galaxies that are old and have no star formation, and therefore would have no Lyman alpha emission. But isn't it weird? I'm trying to find something that I already removed. I've shot myself in the foot from the start. But think about it really close. If I find Lyman alpha in the spectra of a galaxy that is not supposed to have it, then that light didn't come from that galaxy, but behind that galaxy. And now I have found a gravitationally lensed Lyman alpha emission galaxy that we can study in great detail to better understand galaxy evolution. And here is a spectra of a gravitationally lensed Lyman alpha emitter, if anyone is curious. That bright peak you see sort of in the middle is Lyman alpha. And the rest of the spectra is what you would expect of an old non-star forming galaxy. And so to just finish up, my goal right now is to continue compiling a list of these so we can follow up on them with better observations from the Hubble Space Telescope and other phenomenal telescopes so that we can study early galaxy evolution. But I hope everyone enjoyed listening, and now once the bars open back up, you can tell your friends all about gravitational lensing and redshift galaxies like I do. So thanks again for listening, and thank you to Astronomy on Tap for allowing me to speak. So I guess if there are any questions now, I can attempt to answer them.
Thanks, Isaac. That was an amazing talk. I really enjoyed that, and not just because we work together and I was already excited about what you were working on. So first up, I wanted to give you an opportunity to kind of talk about how you're graduating right now and you're starting your PhD in the fall at UW-Madison. Do you have an idea of what you're going to study, and is it related to what you just talked about?
Yeah, and I forgot to throw up the Wisconsin symbol. I meant to throw that up when I said Wisconsin, so
you have to do the hook 'em horns for now, and next week you can do the.
I gotta represent both. Yeah, there's kind of a middle ground between being too interested in too much versus being so like isolated in what you do, and so I'm trying to stay in the middle, meaning I'm having an open mind about research that I want to do. But I also have major interests like galaxy evolution, reionization, cosmology, stuff like that. And when I was at my Ohio State visit, one of the professors said, if you're not interested in a topic, it's because you know nothing about it. And I laughed at that, but then I thought about it more. I was like, well, maybe that is true. And so I'm trying to keep an open mind going in, especially the first 2 years before you start, your thesis. So I have my interest, but I'm fine with testing the water some the first few years, just to get experience, because I don't want to be isolated in astronomy. I want to connect bridges and connect ideas.
That's a really good attitude to have. And I cannot wait to see all the things that you do in the science that you are able to accomplish. So we have some questions for you from the comments. So first up, we had a question from Robert, who was asking about, in the table where you showed like the distinction between like time travel, light travel time, and your distance to an object, how come that is not a linear relationship when you're talking about redshift versus like
so since I was trying to get into that, redshift is confusing. So it's the linear relationship, or the non-linear relationship, pretty much comes from the cosmology that is at play. And when I say that, I mean, you hear all the time that 75% of the universe is dark energy, 27% is dark matter, the rest is regular matter. That is cosmological parameters. And so it's depending on the expansion of the universe of that. If you notice that the time after when it was emitted was not the same as the distance to it. And that's because the universe has been increasing in its expansion rate, which is a whole thing in astrophysics that we're trying to get to understand. So why is this happening? And so a lot of that factors in to why redshift doesn't just, like 0 to 1 is not the same as 1 to 2. What is nice, though, is that when dealing with redshift and when we're looking at spectra, the higher redshift you go, the more spread out your spectra becomes. But that does spread out by the same. Ideally, it spreads out by the same. And so that makes it nice, because then even if we're at redshift 10, we can look and see that the ratio between these, we can pinpoint, be like, okay, this is the spectra of that. And so it's not hard everywhere. It helps us out some.
Sometimes it's a good thing. Sometimes it's a useful thing that it's not a linear relationship.
Yeah.
Also, redshift 10 spectra would be amazing. So cannot wait.
Yeah, I realized when I said redshift 10, I was like, oh wait, that's really high.
Redshift 10 is like over 13 billion years ago, for people who are listening, and that would be really great, and some of the things that we study in our group. All right, so we have another question, and we have a couple questions actually, so I'm going to kind of combine them. So Alan and Charlie both asked a question about how the redshift is impacted by the expansion of the universe. And so is it more impacted by the expansion of the universe? Is there like an object's gravity that gets in the way that changes your redshift? Or is a galaxy that's like moving less redshifted because of expansion if it's going in the opposite direction as the expansion?
Yeah, there's a lot at play that I guess I can't dive into, because I could talk for hours about redshift by itself. But an example is like Andromeda, which is our nearest neighbor, and a picture that I showed. A lot of people know that it's approaching us, and so technically it has a redshift value that's negative, and that's because it's blue shifted and it's approaching us. And so like redshift has a lot of like factors at play, but there's if you want to dive in on your own accord, also if you look up like redshift versus distance, or redshift versus like a time scale graph, you can kind of see how the curves on it aren't they're not just this. And that, so their questions are, yes, a lot of stuff factors in that. If we look at this supercluster, we look at the great attractor, that things might be moving away faster than they were just based on the expansion of the universe. But we're also looking like so far back in the very like crucibles of galaxies that we're looking at, that it's It's more just based on the time after the Big Bang is when we typically talk about it. Some of the more local effects aren't exactly at play, but they are there.
Yeah. So, I mean, redshift is a complicated concept. The reason it's not linear, like you said, is because there's a lot of stuff that goes into play, including the expansion of the universe.
Mm-hmm.
And so if you're interested in more information about it, maybe we could find a good link and we can share that in our video for everyone.
I thought about putting a plot of that on there, but then I was like, it's hard to dive into something and not just keep going. I couldn't find like an endpoint to stop talking about redshift. So, yeah.
Well, you did a great job. Thank you so much, Isaac. Congratulations again. Stick around a little bit later. We have some more questions that we weren't able to get to, but we'll try to do that at the end of the show.
Okay, thank you.
All right, next up, everyone, we have our favorite segment. It's Astronomy in the News time. So we have What a Merger Jr., Jackie Champagne, and It's a Trappist, Danny Krolikowski. My amazing classmates here at UT, if you could go ahead and take it away.
Hello, hello. Yes, of course.
Hello, everyone.
Hope everyone's doing well. Let's get this started. Boom, boom.
So let's get started with Jupiter. Can everyone hear me? I don't know if my microphone is working. Can you hear me, Danny?
I can hear you, yeah.
Okay, great. Okay, so just as Stevie Nicks predicted, lightning strikes maybe once, maybe twice, and maybe 3 times on Jupiter. Recently, astronomers led by Dr. Michael Wong at UC Berkeley released one of the most incredible images of Jupiter that we have ever taken, and it is the sharpest that we have ever seen at infrared wavelengths. This mosaic is made up of 9 individual tiles that are each composed of hundreds of exposures that were taken with the 8.1 meter Gemini North Observatory atop Mauna Kea in Hawaii. These were taken with the NIRI instrument, which is short for the Near Infrared Imager. This imaging process is called lucky imaging, where the star, or here a planet, cries in her lonely heart. No, wait, that's Britney Spears. Lucky imaging is the process of taking
karaoke song.
Lucky imaging is the process of taking hundreds of very short-term exposures with the hope that the atmosphere remains stable on short enough timescales not to screw up the image. So turbulence in the atmosphere will cause images to blur over time, like you're seeing in this left-hand image over here, sort of like that oasis effect on a hot summer day, or maybe just a day in April in Austin. But with many short exposures stacked together rather than one long exposure, one can get incredibly sharp images during the times when the clouds and the water vapor just chill out for a sec. So these observations are in concert with the Hubble Space Telescope imaging Jupiter in the UV, and Juno, which images Jupiter in the radio. So previous UV images of, for example, the Great Red Spot, could see that there were clouds on Jupiter, but we lacked the resolution and the atmospheric transparency to see where the clouds were thin, thick, or simply non-existent. Juno has the amazing ability to detect whistlers, which was coined for the whistle-like feature that pops up in Jupiter's radio emission when there are lightning strikes. So by following up the locations of these radio whistlers in the infrared, we were able to truly discern the actual cloud structure for 2 reasons. So for one, Gemini North is able to achieve 300-mile resolution on these images. So according to the lead Gemini scientist, Andrew Stevens, this is like being able to tell apart the 2 headlights on a car in Miami if you were standing in New York City. The second reason is that the infrared light, which is originating from Jupiter's internal heat, is able to travel through the clouds, unlike the UV light. So that allows us to see in unprecedented detail both the thin and the thick clouds. So these observations allowed for some incredible conclusions about Jovian meteorology, including that the Great Red Spot is not a spot at all. It's actually a gap in the clouds where Jupiter's insides light up like a jack-o'-lantern. These lightning strikes are 3 times stronger than any of the super bolts we've ever seen on Earth, and they come from thunderclouds over 5 times taller than the ones we see in our own thunderstorms. Lightning strikes mostly originate from the poles, which is opposite to how storms occur on Earth. And finally, these clouds originate from deep clouds of water, ice, and also liquid water in great convective weather cells. And there are even filamentary cyclones. So I guess my dog should consider herself lucky to be a resident of Earth. Imagine all the howling that we would get if thunderstorms were as loud as the ones on Jupiter.
I'm just thinking about all the amazing glass that we can make with those lightning strikes.
Ooh, true.
Watching Sweet Home Alabama on repeat back in the day. So shifting gears a bit, so picture this, right? In about 5 billion years or so, the sun will have expanded in size to become a red giant star, right? So big that it will have engulfed Mercury, Venus, potentially the Earth, before shedding its outer layers to become a white dwarf, basically the remnant of the sun's core that's hot and only about the size of the Earth. So, I mean, I guess if you think as a human, that's not a particularly rosy picture, granted, if we could even make it that far. But we can't imagine that would be good for life as we know it on the Earth. But as with anything regarding habitability in the universe, perhaps we should stop being at least a little egotistical as we are as humans and expand our view of what habitability might mean in the universe. And if we do that, the era of a white dwarf sun might actually not be so bad. Could planets that still exist orbiting a white dwarf after it becomes a white dwarf be habitable? Well, work led by Dr. Thea Kazakis from Cornell University, who's actually also a good personal friend of both Whataburger Jr. and myself. And also
newly minted, a doctor as of 2 weeks ago.
Yes, 2 weeks ago, successfully defended her dissertation, so congrats to Thea. She has been doing work looking exactly into this. Could life exist on a planet around a white dwarf? And so first, Dr. Kazakis showed that the habitable zone around a white dwarf, right, so where a planet could exist with liquid water on its surface or the right conditions for life, is actually remarkably stable, much more stable than it is around a main sequence sun-like star, something like up to 8 billion years, which is by far enough time for life, complex life, potentially even intelligent life to form. And on top of that, her most recent study has also looked into, well, let's say this life exists, would we be able to detect it? And the results are actually quite promising. So how would we go about trying to detect life on a planet around a white dwarf? Well, we would want to look to see what's in the planet's atmosphere to look for signatures of life called biosignatures, right? And we would do that by seeing when the planet transits in front of its host white dwarf and to see how light changes passing through its atmosphere to figure out what is in the atmosphere. And there's an added bonus that since a white dwarf is roughly the same size as the Earth, the transit signal would be huge. Normally we go on and on about how hard it is to detect atmospheres of terrestrial planets because the signal is so small, but around a white dwarf, the signal would be much larger. And so by fully simulating what a terrestrial planet's atmosphere would look like around a white dwarf, which is extremely different than around a sun-like star, she actually finds that we would definitely be able to detect biosignatures like methane and oxygen with next generation telescopes like James Webb. So Rebecca, if you're still drinking at the James Webb references, go right ahead.
Now, so much drinking. So much drinking.
Now, of course, this is not without complications. We haven't found a planet around a white dwarf yet, but that's because it's really hard. Because of the white dwarf's small size, the likelihood that a planet transits would be quite small. But I mean, hey, right, I mentioned that human ego earlier. It can be good for some things, like it makes all of us scientists extremely stubborn enough to search for something until we find it. And so I think that since life finds a way, I truly believe it's out there waiting to be discovered, just like Dr. Kazakis has predicted.
It's kind of spooky. I'm waiting for the alien descent. And you might be worried by this headline that a black hole is coming to chomp you like Pac-Man, but not to worry. So social distancing, kind of a bummer, right? What if we had to socially distance in a straight line? I did this math. I did it right here on the back of a receipt. I figured out that the entire human population would span about 60 billion feet, which is about a millionth of a light year. Imagine lining us all up 87,000 more times, and you'd just be getting close to the closest black hole ever discovered, as announced by astronomers last week in the Astronomy and Astrophysics Journal. So Thomas Ravinius, who is an astronomer at the European Southern Observatory based in Chile, led the study of a triple orbit system observed with a 2.2-meter telescope at La Silla Observatory. So this is only 1,000 light years away in the constellation of Telescopium, which seems like a joke, but that we really called something that.
It definitely doesn't look like a telescope, does it?
No, telescopium sounds like one of those elements that they couldn't come up with another name for. They were like, Einsteinium. But anyways, the Pharos spectrograph took spectra of a known binary star system, which is where two stars orbit each other. So based on the different widths of the known spectral lines, scientists are able to discern that there are two stars present. One is a BE blue giant, which spins so fast it blows out its material with an equatorial disk, and the other is a B-type giant, which is a little less blue and a little more stable. But what else they saw surprised them. There was a wobble in the spectrum causing movement of the expected spectral lines on a scale of about 40 days, which indicates the presence of a third object affecting the gravity of the orbit from a much greater distance than the inner pair. So based on the way that astronomers measure mass from stellar spectra, they deduced that they were seeing an additional object about 4 times more massive than our sun. But wait, there's more. This third star was invisible. Without any of its own spectral signatures, they knew that it wasn't a star like the first two. But what's more is that there were still no bright X-rays, as is typical of stellar mass black holes. Thus, we are seeing the first quiet stellar mass black hole, which could be typical of the configurations of the neutron star black hole binaries that eventually produce gravitational waves during their mergers. So if that's the case, millions of holes could be littering the galaxy. Of course, there are two sides to every story. A competing team of astronomers suggests that this could still be a regular binary system if the masses of the inner stars were deduced incorrectly, which highlights the fact that stellar spectroscopists are not bygone scientists of the past, even though all the stellar spectroscopists I know are at least 80, but it's not a dead science. Because just like Zoe taught us before, imposters lurk among us all the time, not the stellar spectroscopists, but the black holes. But still, the system is pretty cool because it's 3 times closer than what we initially thought was the closest black hole, which is in the constellation Monoceros, about 3,000 light years away. In fact, if you were to hop down to Chile in the near future, which I don't think you should do, but if you really wanted to, this system is visible with a good pair of binoculars. So the black hole is not one of these glorious accretion disk beauties like from Interstellar, but the binary stars are an impressive magnitude of 5.4, which is a bit brighter than Uranus, which is perhaps an unfortunate comparison when talking about black holes. But these are exciting times in the world of black hole astronomers and those interested in gravitational waves.
Pretty cool. So now for some astronomy out of the news, but a bit closer to home than that black hole. 2 new, young, and evolving exoplanetary systems have been found with the TESS, Transiting Exoplanet Survey Satellite Mission. These systems were found by the THYM collaboration, THYM, TESS, Hunt, for young and maturing exoplanets. This is one of the rare astronomy acronyms that I actually think is quite genius, of which multiple UT astronomers are members, including Dr. Aaron Rizzuto, who is a 51 Peg B fellow postdoc here at UT, and who led one of these discoveries, and Dr. Andrew Mann, who is a former UT postdoc, now assistant professor at UNC Chapel Hill, who led the other. So, okay, we found 2 young planets. That's cool. But finding planets around young stars is, well, just, it's really hard. Young stars are extremely noisy, I guess, not unlike their human counterparts. Their brightness changes a lot. They're spewing out material. They're rotating really rapidly. So yeah, I mean, really.
Also not unlike a baby.
Oh, spewing material. Oh boy. So this plot that's shown on the screen is a test light curve of one of these stars, and that up and down is a change in brightness by the star itself, way larger than a transit of a planet, right? TESS finds planets by seeing dips in brightness when a planet passes in front of its host star. So because a young star is so noisy, it makes it really hard to find planets. But luckily, we have really smart people like Aaron and Andrew who can figure out how we might be able to dig these signals out from the mess of a young star's light curve. Now, okay, so if it's so hard, right, why do we want to find young planets? Of course, other than that scientific stubbornness I mentioned earlier, well, our understanding of how planets form and evolve is really still developing. And observations of young planets is really necessary in our efforts to form theories of planetary formation and evolution, right? And we need to find planets of a variety of ages, really many ages crossing the first billion years of its lifetime or so, because we can't just plant a star in our backyard garden and wait the billion years for it to, you know, form a planetary system and see those planets evolve, right? We can't do lab experiments. So we need to find young planets out there to study. So these 2 planetary systems are really cool. One of them is around a star that's only 15 million years old, which is extremely young in the grand scheme of things. It's actually the youngest transiting hot Jupiter-sized planet ever discovered, which actually means it's very, very promising for follow-up characterization with something like, sorry, Rebecca, the James Webb Space Telescope. It also shows that these hot Jupiters, some of them must either form really close to their star, which we thought wasn't possible or unlikely, or they must migrate really quickly, right? If that planet's there in 15 million years, it needed to have moved in 15 million years. The other planetary system is around a star roughly 400 million years old. So not quite so recently formed, but still at an age where it's actively growing and evolving. Now, these are just 2 systems. Luckily, TESS will continue finding more and more young planets of a variety of ages, allowing us to map out how exoplanets change through their early evolution without having to wait those billion years needed if we were to plant a star system in our backyard garden and see how the planets grow as they evolve. Awesome.
Sounds like a fun gardening project.
I mean, well, I guess with quarantine, you got enough time, so. Cool, well, that's all we got for the news this month.
Thanks, everyone.
Hope everyone's doing well.
I know I'm starting to lose my mind, but it'll be over.
Space gardening sounds like my next new adventure.
Oh, your apartment doesn't have room.
For space plants? It sure does, totally.
Right,
thanks, bye, everyone. Amazing, as usual. Stick around if you have any questions about any of the news articles. They will be around after the end of our show. If we could have Dustin turn on your video, please. So our last speaker tonight is Dustin Katzberg. He'll be talking to us about outbursting white dwarfs and the homogeneity of binary star systems. Oh, Kira's here too.
Hey, Rebecca.
Dustin is a senior astronomy and physics major at UT Austin, and before enrolling at UT, he was a submarine sonar technician for 7 years while being based in Connecticut. And still today, he is involved in the Navy Reserve's submarine community. At home, he is a super lucky father to his daughter, Kira, and a husband to his wife, Victoria. So shout out to Kira for joining us. And Dustin, if you are ready, go ahead and take it away.
Yeah, for sure. Kira wanted to do a quick cameo, say hi while she could. We thought it was appropriate since the universe created her, and we all study the universe.
Perfect.
So there we go. All right. All right, so I'm going to split my time up talking about two different subjects, kind of like how I split up my time at UT Austin. So when I first got to UT, I entered into a pipeline, that focused on studying white dwarfs. And after a year and a half of that, I kind of shifted gears and started working directly with a professor at UT, Dr. Keith Hawkins, who is a galactic archaeologist. So that'll sort of be the second half of the talk. All right, so kicking off with the first half, what exactly is a white dwarf? Well, over here on the right, we have a color magnitude diagram. Color magnitude diagram is basically an overview of the entire life cycle of a star. So here on the x-axis, we have less massive or cooler stars, or more massive bluer stars to the left. And then y-axis, we have luminosity or magnitude. And so as a star begins its life, it begins to fuse hydrogen in its core, and we call this the main sequence. It spends a great deal of time on the main sequence. Now, depending on the size of the star, if it's really massive or if it's less massive, which for this talk we'll say above or below about 10 solar masses, about 10 times the mass of our sun. If it's more massive than that, then it will go through another phase where up here, if you can see this tiny little onion, after it's done fusing the helium in its core, it leaves, or the hydrogen in its core, it leaves helium as a byproduct. It's massive enough such that it could also fuse the helium and leave a byproduct of carbon, et cetera, et cetera. I'll do that for a few more elements. And eventually, though, if it is massive enough, again, it will earn itself an iron core. No star is massive enough such that it can fuse iron. At that point, it is energy inefficient. And so this beautiful equilibrium that we had for so long, where the star was outwardly pressing energy via fusion, balancing against the gravity that was pulling it inward, gravity will win. And so the star comes crashing down in on itself in a very short amount of time, and heats up in a very short amount of time. And that's how we get our supernovae. That's for the very massive stars, which are not the majority of stars in the universe. The majority of stars are actually less than this 10 solar masses. I'm not sure if you can see my cursor, but I'm using it to point out stuff. So the majority of stars actually go through a very similar process, but with fewer steps. So we go through our main sequence where we fuse helium and hydrogen, but after that, we sort of collapse in on ourselves and shut out our outer layers into those beautiful planetary nebula that everybody has seen beautiful pictures of. And instead of the remnants of a massive star where we have a neutron or a black hole, we have instead, as Danny mentioned a little bit ago, a remnant of a white dwarf. And again, the size, like that's what our sun will end up being one day. A star about the size of the sun will end up being about the size of the Earth as it spends the rest of its life as a white dwarf. So a quick slide about Kepler. Kepler was launched in 2009 to find planets, and it did an awesome job at that until it stopped working. But not to worry, brilliant scientists and engineers figured out a new way to utilize it, and just a handful of months later, it was sort of repurposed for what they called a K2. So what that ultimately meant is that Kepler had mitigated ways of maneuvering, and so it was sort of stuck, if you will, at staring at individual portions of the sky for long periods of time, roughly 3 months or so. Whoops, let me go back up. And while this was perhaps bad news for some of the astronomy science community, it was good news, at least for the white dwarf community and a few others, because again, white dwarfs, while they are very, very hot, they are also very, very faint. And so you need to stare at them for a while if you would like to see them. So Kepler was great for the white dwarf community. One characteristic about white dwarfs, they happen to pulsate at these fundamental frequencies. So when a white dwarf is first born, it's, again, this last stage of evolution for a star. It's born, it's some temperature hot, and it's not going through fusion or anything anymore. And so it's just sort of gonna kind of sit there and slowly lose, expel heat for the remainder of its life for billions of years. A couple different types of white dwarfs. We have predominantly hydrogen atmosphere white dwarfs or predominantly helium atmosphere white dwarfs. And for each of these, there's slightly different size windows and temperature, where as that white dwarf cools, it actually, as it enters this window, it pulsates a little bit. It pulsates at different fundamental frequencies. And so what astronomers who study white dwarfs do, they're actually able to use these pulsations to study the interior of white dwarfs, which they dub similar to geology, geologists on Earth, they dub astroseismology. So one step closer to what we did for this project, what I did for this project. In as recent as 2015, astronomers started to notice that these white dwarfs actually, some of them, a small community subset of them, get bright for some reason for a short period of time. A short period of time, maybe roughly a day or so. And so astronomers dubbed these outbursters, or outbursting DAVs and DBVs. And by brighter or more luminous, I mean roughly 4 to 15% brighter, although in some cases there was even upwards of 40% brighter. However, nobody knows why this happens, but they do believe that it was related to these pulsations. So this brings us another half a step closer to what my project was on. But I'm going to introduce two basic plots before we get to the finale. So pulsations are what we're looking at, right? So this is a Fourier transform plot. And what that means is on the x-axis here, we have frequency in microhertz. And on the y-axis, we have amplitude. So for this particular star that was observed with Kepler during the K2 campaign, as you can see here, all these peaks represent various fundamental frequencies for the pulsations, all within this one singular star. And then in the top right, we have a slightly more intuitive plot, which is simply time and days here. This is about 3 months or 82 days. And then on the y-axis, we have flux or intensity or brightness. And so you can see these little spikes here. These represent the outbursts that I was talking about. And so there's a little over half a dozen or so of these outbursts over this 3-month period. One other note about this Fourier transform. So there is time in this graph also, but it's in the z-axis, if you will. So all 82 days are kind of stacked in the z-axis, and this is the sort of averaged out Fourier transform of that. So real quickly, I'm going to take you to this other screen. This was the result of 2 or 3 months of coding by a sophomore. This is that same Fourier transform 82 days that I showed you. And on the bottom right, we have the same 82 days of the light curve. Now that, one point I was going to make. So the question then is, what, again, we believe that these outbursts, we don't know what's causing them. However, we do think that they are somehow related to the pulsations, to these fundamental frequencies of the white dwarfs. So, well, maybe we should look at a Fourier transform, an FT plot of just before an outburst, during an outburst, and after an outburst. But rather than juxtapose just a few plots, why don't we juxtapose a whole bunch of them and make a digital flipbook, if you will, or a movie. And so that's what we did here. On the top right, we have sort of a 5-day zoomed in window, which you see here reflected in the bottom right also, and then a 1-day window, if you will, that's sort of zoomed in on this outburst here. And then to the top left and top middle, we similarly have a 5-day Fourier transform movie and a 1-day Fourier transform movie that is going to look significantly different from the averaged out Fourier transform that spans the 82 days of the light curve that we saw on the previous slide or in the bottom left of this here. So I'm going to play this just for a few seconds so you could sort of see it in action. And as this goes over one of these outbursts, generally speaking, we could see the Fourier transform change and it gets higher. And then after it exits, it goes back to its normal sort of average 82 day. Shifting gears super quickly to the second half of the talk, galactic archaeology. What is that? Well, galactic archaeology aims to utilize studying the chemical makeup and age of stars in an effort to describe how our galaxy, the Milky Way, formed. What is a galactic archaeologist? This in the bottom left. This is Dr. Keith Hawkins at UT. He is my research advisor. He in every way led all of the research on this project and gave me the opportunity to walk with him and participate and learn a few things along the way for some of the work we did for this project that I'm going to spend a few slides talking about. So one of the postulates in order to understand this, the formation of the galaxy, is that we need to know are stars that are born together chemically identical. Now, intuitively, this makes sense. If you have a bunch of matter in one spot, it's made up of the same stuff. It coalesces into a couple stars. Sure, it's going to be the same. However, in at least one case, this was not the case. This is a paper that talks about at least one example where they found that a couple binary stars were not at all chemically the same. And they cover a handful of interesting reasons why that may be. So we needed to give some sort of weight to this statement that sure, of course, all stars born together are the same, but to what extent? And so that's kind of where this project stemmed from. This was the Keith's paper that resulted from the project that I got to contribute to. These are a couple of the plots that I got to contribute to. So over here on the bottom left, we have, again, a color magnitude diagram from, these are all stars from the Gaia satellite, which the other color magnitude diagram that I referenced earlier was also of. This is a smaller subset. And we could, again, see the sort of main sequence here going across, and then the red giant branching away. And in the blue and red tied together, we could see the 50 stars that we observed, or that Keith and Maddie Lucy observed. Maddie is a graduate student under Keith at UT also, as is Tyler and Drea, and Megan Thompson here. And I actually worked on this. We're both undergraduates and we worked on this together. So again, on the left, color magnitude diagram, this is just showing the stars that Keith and Maddie observed at UT's McDonald Observatory in West Texas. They did this 2 Januaries ago, so relatively recent. Finally, on the right, we have a plot. This is just, it's the same binary stars, but it's the temperature of these stars measured using 2 different methods. Temperatures derived spectroscopically down here on the bottom, and then the difference between temperatures derived spectroscopically versus photometrically. And I'll get to what that means or why it's important here in just a second. So this is a plot that was 100% Keith, but this is looking at 4 different binary pairs. It may be difficult for you to tell, but each one of these colored lines is actually a dotted line and a solid line, and it represents each star in the binary pair and what all these little dips are. So on the x-axis, we have wavelength in angstroms, or about 10 to the 10 or 10 to the minus 10 meters. And so each of these little dips here represent different chemicals or elements that their absorption lines. And so as we could see, they line up very well. This tells us that these 4 binaries are indeed chemically very similar. This is another really cool plot that Keith made called a violin plot. And what it shows is that, so the top and bottom are very similar, but what we have is the difference in 23 elements, the ratio of 23 elements next to hydrogen on the top, and the ratio of these 23 different elements that we looked at across the, but juxtaposed to iron versus hydrogen. So we could see in the orange that, oops, the chemical abundances of the binary stars is what the orange represents. And the blue or the teal is the chemical abundance differences and ratio differences in one of the binary stars versus some random star. Now this is where that a couple plots ago where I mentioned the effective temperature comes into play. So we don't want to choose just any random star. We actually want to say, I don't know, pick any star here and then pick some other star that's immediately next to it. It's not anywhere close to it in space, but it's right next to it on the color magnitude diagram. So we could say that it's the same mass, it's the same temperature. And so what this plot then is doing is comparing, is showing the juxtaposition between the chemical abundance similarity between the two binary stars and the chemical abundance differences between one of those binaries and some random star that is the same mass and the same temperature. And as you could see, to an order of roughly a full magnitude, the two random stars are very different, and to an order of roughly 0.02 or 0.01 magnitudes or less, they are indeed the same. So that is also pretty much the conclusion, although this was a very small subset of 25 binaries. They all were within 0.01 magnitudes within deviations chemically the same. And so what that means is then binary systems are very chemically alike, which is what we wanted to hear. The stars born together do possess these sort of chemical fingerprints that we do postulate, and which is required for forming some sort of theoretical formation of the Milky Way or any galaxy. So James Webb, James Webb, James Webb. Cheers, everyone. And that's it.
So mean. You're so mean.
I'll drink Rebecca just to make sure that that gets covered.
Thank you.
Thank you, Dustin, for that awesome talk. That was, I love hearing about galactic archaeology. It's such a cool, it's a cool topic with a very cool name.
It does reel in the name.
It's a winner. Okay, so we have a few questions for you. Let's see, one here is, could you use this I think this is talking about the first half of your talk. Could you use this technique to study any other astronomical systems or answer any other questions? I think it's talking about the pulsations, maybe.
Yeah, absolutely. So that neat little video that we wanted to make is not reserved for white dwarfs. It's not reserved for pulsating white dwarfs, outbursting white dwarfs, or anything. It could be used to monitor any star that you were interested in juxtaposing the I guess pulsation frequencies of any stars, because a lot of stars pulsate. All stars pulsate to some degree, but the only reason why we used it or we wanted to build it for outbursting white dwarfs was because we believed that the outbursts were tied to the pulsation periods. But a lot of stars pulsate, our suns pulsate. In theory, we could use the same code and look at a Fourier transform of movie of our sun pulsating as well.
Nice. Yeah, turns out stars are complicated. I like galaxies where you just average all the stars together. Okay, let's see. So now talking about binaries, are there stars that orbit together but didn't form together? I guess, is it possible you could have a binary system of two stars that weren't born from the same cloud, maybe?
I think the answer to that question is in theory, but I think that the likelihood of something like that happening is astronomically small. I think say in that case, yeah, that might be like one of the first ideas that we think of. Well, how are two binaries very different? Maybe they didn't form together. Maybe they were separated, and maybe they joined somehow later on. But I don't think that was even one of the considerations that paper covered. I think maybe that paper focused more on accretion of material from one star to the other. And maybe those stars were at different evolutionary phases in their life. And so maybe that contributed to the difference in their chemical abundances looking so different. But as far as any two random stars, I think that's more of a needle in a haystack sort of thing. There's no way those two are going to find each other, or if they do, they're probably moving at such a velocity that they're going to change each other's orbits, but whip away from each other and not actually be able to stay. But that's my take on it.
Okay, yes, so they might, if they do come in contact, they might not be gravitationally bound. It might be like a temporary.
Right. Yeah. Exactly.
Let's see, another question. Is Fourier transform something you can use for galactic archaeology as well?
No, I don't think so. Nothing comes to mind initially. The three big sort of tripods, if you will, or something that holds up galactic archaeology are chemical abundances. That's a huge thing that we're interested in, is tagging stars for their chemical fingerprint to see, just like humans, all 7 to many billion of us have them. They're all different. Stars are effectively the same. And so that's a really important key postulate in that. And also the other really great thing about Gaia is that it has incredibly accurate kinematic it knows what direction and how fast stars are moving really within great detail. And so doing spectroscopy or finding those chemically tagging those stars with those two sort of powers combined, you could do, or the galactic archaeology community could do quite a bit with Gaia information. But as far as a Fourier transform goes, I can't immediately see what information that would provide.
Cool, awesome. Okay, thank you. Thank you for awesome talk, for answering these questions. I think we're going to, Rebecca and I will close out the show here, and then we'll call all of our speakers back after we do a quick summary, a quick conclusion to answer any additional questions you have. So keep adding questions to the YouTube channel or to Twitter if you still have them and they haven't been answered yet. And we'll call all of our speakers back to get those done in a few minutes. Thank you again, Dustin.
Thanks, Michaela.
Thanks, Dustin. All right. So like Michaela said, we're going to do a quick closing. So normally during our show, we would go through all the trivia answers, but we wanted to give you some extra time to do trivia and also allow for people who weren't able to watch our show live the time we're streaming it right now to play trivia and also get a chance to win. So we will announce those trivia winners through our social media, and we'll also email the people who won at the end of the week. So stay tuned. We'll post all the answers on our social medias, and we will let you know if you won.
And that means if you're watching this show not live, but later, you have until Friday, ish, when we remember to turn the trivia off.
We're doing a great job. So a big thanks to the North Door for being a great venue that we would normally be in the middle of. Shout out to all of tonight's speakers for doing a really great job. Especially a big shout out to our space cadets, those people in the background that make this show happen that aren't necessarily on camera right now. There's a lot of them in the chat, so please thank them for moderating, for combining questions for us, for posting on social media, and for genuinely being great humans. Thank you to the AoTATX committee. Without you, we wouldn't be here. And
thank you to you, the audience, for tuning in and sticking with us and coming back to check us out each month. Tell your friends, and let us know in the survey what else you'd like to see content-wise from AoTATX.
Yes, let us know. While you're thinking about Astronomy on Tap, please also think about the North Door and Pueblo Viejo. Again, we're putting the link up here for you to help chip in and support the staff, the bartenders, the door people, the cooks, everyone at our venue who is no longer getting revenue right now. So please join us in supporting them. If you would have normally bought a taco or a beer, maybe think about donating that amount of money to the staff so that they can survive during this difficult time.
Our next show is going to be another special show. We've got a summer of cool special shows for you set up. So our next show, AoTATX number 69, is on June 16th. This time, same place, your living room couch. We will be hosting a geophysics takeover show. So we've got geophysicists from a different department of UT who are going to come and talk to us about space radar, ice in space, and asteroid impact. So it's going to be a little different than one of our normal shows, but really exciting and very cool.
Yes, shout out to geophysics people for doing stuff in our own solar system. We don't know anything about that. All right, in between shows, please connect with us on social media. We have a YouTube channel, which you are currently watching right now, so please go ahead and subscribe to that. You'll see all of our live shows as we post them, but you'll also be able to watch all of the other talks that we've given in the past, minus the ones that we haven't quite managed to upload yet from last year, but all of those videos are there. Fill out our survey if you'd like to see us do more / different things. We're on Facebook and Twitter and Instagram. We have a website and an email address, and so we have all kinds of ways for you to reach us. If you have any questions or comments or concerns, please let us know. And that is all we have for our main show. If we could get all of our speakers to come back, we do have a couple more questions. If you had questions for the speaker that weren't answered during the general talk question and answer sessions, please post those in the chat, tag us on Twitter or however you're sending in your questions, and we will be sure to ask those to our speakers. If you had questions about the news, we'll do our best to answer those. Or if you just have other questions for us, please just drop those in the chat and we will ask those in the panel. And if Jackie and Zoe could also come back whenever you're ready. Perfect. All right.
I think we can start off just because I found a question and
okay, good. I was like,
I found one. We're sifting through a bit here. So I have a question for Isaac from Jeff. How many galaxies are red shifted versus blue shifted?
Well, that's a really good question. And actually, when I first started getting into astronomy in like high school, that was like, I remember one of the first questions I actually like looked up because I thought it was really strange. But overwhelmingly, the vast majority are being redshifted. And most things that are blue shifted are entirely based from like local effects or gravitational effects that we kind of touched on. So like Andromeda is going to collide with us. It's being blue shifted. That's the gravitational effects between the Milky Way and Andromeda. When you get to superclusters, the gravitational binding that's taking place, you'll have ones that are colliding versus not, but overwhelmingly vast majority are being redshifted. So it's entirely local effects are causing blue shifts pretty much.
No, good to know. I have a very science-related question for everyone. Actually, for Michaela. Rajesh's son wants to know if those things behind you are swords.
Oh, yes, they are.
Why do you have swords, Michaela?
So I practice a Korean martial art called Haedang Gumdo, which it's basically sword fighting, and it's awesome. You should look it up and find a dojang near you that teaches it. Yeah, so I have 3 swords, and the first one is a practice sword made of wood. The next one is a practice sword that it's like a full sword, but it's dull. And then the last one is sharp. It's very sharp.
Sharp is sharp.
Real sharp. Anyway.
Okay. I wanted to ask this to our two undergrads who are not graduating this semester. Hang in there, you're almost done. What are your plans for the future after you graduate, or even just during the summer while you're not in school? Make sure you unmute yourselves.
Do you want to go first, Dustin, or?
Sure. So typically during the summers, yes, I'm a senior, but I have at least one more semester left. And typically during the summers, I play that Navy Reserve game that Rebecca mentioned. So if I'm lucky, I'll get to go to Washington and play with some unmanned underwater vehicles for a few weeks. I'm also, I normally don't do any schoolwork during the summer. This time I'm taking a differential equations course at ACC to help increase my chances of graduating from UT next semester. And afterwards is not very astronomy related. I'm sort of a bit of a different undergraduate community, as you saw Miss Kira earlier. So Victoria and Kira, I think, are probably going to move to Colorado and sort of do like some family stuff for a while and focus a little bit more on her occupational therapy school. And in the interim, I'll keep doing Navy Reserve stuff, but I am most definitely looking into astronomy departments at Boulder, Fort Collins, that area. And if all cards are on our side, then maybe able to kind of shift into that role a little bit. But that's sort of a limiting, realistically speaking, that's sort of limiting my postgraduate options.
Yeah, that's understandable. I mean, there's a lot of things that are important in life, and family is on the top. So, what about you, Zoe?
Yes, so for this summer, I'm with family in Washington, D.C. And I'll probably just be quarantining here for the next 2.5 months. I'm taking a math class on probability, and then I'll continue working on the ExZoPlanet research remotely. So yeah, I'm really lucky that like I can still do the science I like to do just from my computer. So I'll be kind of doing that this summer, and then I have an entire year left, but I'll be applying to PhD programs this fall.
Awesome. Well, good luck to you. I think we have some other science questions, but also news-related questions. So I believe we have a question from Rajesh, and I'm not sure who wants to answer this because it was about one of the news articles, but how do you know if a planet is young? Is it because it revolves around a young star?
Yeah, sure. I can talk about this. Yeah, that's a really good question, and something that we think very, very carefully about. But yeah, precisely that, right? The age of a planet is basically the age of its star. So if the star is 20 million years old, the planet's 20 million years old, give or take a few million years. So what we do is we look for planets in associations of stars. So these are either more like traditional star clusters like you think of, like the Pleiades, the Hyades in Taurus, those because you have a lot of stars that you can look at and they're all the same age. It's a lot easier to figure out how old the star is. If you just kind of pick a random star out of the sky, it's really hard typically to figure out how old it is if it's above maybe like 1 billion years old. And then we also have moved because, there's only so many of these clusters to looking for like looser associations of stars. So these are stars that all form together, but because of, motions in the galaxy and just how stars evolve, right? Like the sun probably formed in an association like that and then it dissolved. And so we also look for planets in these looser associations of stars. But even there, right, I mean, a lot of these papers there's a significant portion that's given to how we figure out how old a star is.
That's cool. Michaela, do you have any?
I have a question for Dustin. How many candidate siblings of the sun are known?
How many
Candidate siblings of the sun are known? I'm not sure whether they're referring to perhaps like how many stars like the sun there are, or maybe like did the sun have some birth siblings that we know about? So I suppose you could choose which one you'd like to.
We could choose. Yeah. So, I mean, our quick little bullet that we had, I don't know where the ratio lines fall at 8 solar masses, 6 solar masses, et cetera. But just with the vast majority of stars in the universe that will end their lives as white dwarfs tells us that the vast majority of stars are less than 10 solar masses, which the sun is. The sun is a very average star. I think it might be slightly on, just barely on the less massive side, but not by much. But at the same time, when we're talking about trillions of stars in the universe, is incredibly common. Yeah, it's my knowledge. Well, wait, what is this? This is common knowledge. Like, what is the nearest star to the sun? It's not very near. It's relatively near, but it's not. It's not like within binary distances. So no, the sun never had. I don't think, as far as anyone knows, like a binary companion.
I have a question for Zoe. Yes, here. Are there tasks in astronomy that are not well suited to AI? Like, I guess, are there questions or tasks that you think will always have to be only human?
Yeah, so there's certain kinds of problems that lend themselves well to AI in general, and those are problems that have really large data sets. So if you had a specific, I guess if you had very little data on something, then you can't really do a good job of actually studying it with AI, and you would have to look at it more from a theoretical standpoint, or maybe kind of modeling the data more with astronomers looking at it rather than feeding it into one of these machine learning systems, because if you don't give it enough different examples, it kind of tends to not be able to generalize well, and it can't actually do a good job. I'm trying to think if there's some specific examples of that. Because the research that I've done specifically lends itself well to AI. But I'm trying to think if there's some examples of. Okay, I can think of one thing. So for the X-ray binary stuff that you were talking about, where we had the black holes and the black hole imposters, there's some of those examples where the source behaves really strange. And it's very different than any of the other kind of black hole systems that we've seen of these binary systems. And in that case, if we only see one example that's really unique, it doesn't really help to use machine learning. It would help a lot more to use other tools, like some of the math that we can understand, or some theoretical models to actually understand what is happening physically. And machine learning probably won't work really well because we've never seen anything like it before in that case.
Cool. I have another question for whomever. We had a lot of talk about binary stars and binary stars with planets potentially. Have we found Tatooine yet? If anybody wants to chime in.
Yeah. Yes. We have found planets.
Is that a Star Wars joke?
It is.
Jackie, watch the Star Wars.
I don't know Star Wars. I know Baby Yoda.
Yeah, we have found planets in binary star systems. So yeah, is the answer. I mean, it's a lot harder, right? Like if you're observing the transit, then you need to get the transit out from the stars eclipsing each other, and the planet could transit both of them at the same time, and they could all line up, or it can transit one and then the other. And with the radial velocity, you'd be picking out a pretty small planetary signal out of a potential larger signal from the stars orbiting each other. I actually don't know. I know all of the circumbinary planets I can think of have been found with transit. So I actually don't know if any have been found with radial velocity before, but please correct me if I'm wrong. But yes, they can. But it's a lot harder also for the orbits to be, stable. There's less stable orbits possible, and whether life could arise there, who knows? The climate would have to be stable, which is potentially not likely.
We have, I think, another question for the news. And I'm curious too. So regarding the Lucky imaging, is that what TESS does? Is that how TESS is working? Or how similar is that to what TESS does?
I don't know. Oh,
cool.
Well, so I mean, right, Lucky is designed to mitigate issues from the atmosphere, right?
Well, I mean, the point is that it just like rapid fire takes a lot of short exposure pictures.
Okay. Because if part of that is to mitigate issues from the atmosphere, TESS is in space, so it doesn't have that issue. But also, I don't know. TESS does have different exposure lengths, but I don't think it works like that. I think it's 30-second and then 2-minute exposure, something like that. But also, TESS's pixels are like ridiculously large also. So kind of any noise introduced there wouldn't matter as much.
Can't be worse than Arecibo, which is a single pixel camera.
Radio is weird.
The Arecibo is a single pixel camera?
Yeah.
How? No, I don't know if I want to know. No. Never mind. I don't know if I want to know.
Rebecca, how can you complain about a single pixel?
My galaxies are 2 pixels. Thank you. Maybe 3.
3 whole pixels.
3 nice, beautiful, wonderful, ancient pixels.
Yeah.
We have another question that, is up for grabs. So when you have planets around binary stars, do they revolve around both stars?
I guess this is me again. Yes. Right. You could imagine planets that orbit around both of the stars. So the 2 stars are orbiting like this, and then that's orbiting both of them. Or you could imagine maybe a planet orbiting one of the stars and then the other stars going around it. Kind of those like classical circumbinary planets you're thinking of. I want to say most of them, they orbit both of them, that's a more stable orbit. Now I could imagine like that's like for close stellar binary. If you have kind of wider systems, I'm not sure. That would probably be more stable, right? I mean, technically Proxima Centauri, the closest star to the Earth, is technically, in a wide triple system with Alpha Centauri, which is 2 stars that are much closer together. So I guess that's in some sort of a multiple star system, but Proxima Centauri is much further out than the central stars. So it's not quite the same. But I can't say like numbers off the top of my head, how many, if any, orbit just one in a close binary. But I think that orbit would be a lot less stable than an orbit around both of the stars if they're close together.
Sorry, we're looking at like 50 screens right now.
Sure. Give us a sec.
Okay. Oh, thanks, Will. Will is answering some of the test questions in the comments there. Will is a postdoc at UT. I think we have less science related questions, but I think we have one more science question that I see at the moment. So if you have a second star in a binary system, how does that impact the habitable zone? Is that a thing where you need to be like far away from both of them, or how does the habitable zone change when you have multiple stars in your system?
Yeah, absolutely. It would change it a lot, right? I mean, that's the thing with life on a circumbinary planet, right? The whole, life needs stability to, develop and really, well, to thrive and kind of evolve. And so you have an issue with binary star systems that you would need the configuration to be such that the climate is stable for a significant period of time, right? I mean, if we were thinking of something like life on the Earth, right, the climate would need to be roughly stable, right, for 4 billion years, right, for intelligent life to form. Roughly stable, meaning that we've had, large swings in climate before, but binary systems could be worse. Yeah, so I could imagine if you're in a system orbiting too close in stars, right, your habitable zone would be further out than it would otherwise be around any one of those individual stars, just because there would be more sunlight. But you can do some really wacky stuff with like planets in binary systems. Like there was a paper, I don't think it was actually an April Fool's paper, because I want to say all the science was roughly sound. But someone did like a thing where they mocked up a planet in a binary system such that basically recreating the inconsistent and like long or short winters on the Game of Thrones world.
Oh, I read this.
Yeah, and so like, with the right configuration of a planet in a binary star system, they were able to make it such that like sometimes winters lasted, 6 months, and sometimes they lasted like 5-10 years or whatever. So you can get some really wacky stuff with binary stars. It's just I think the hardest thing is making sure that the orbits are stable and that the kind of sunlight that you're receiving is stable for a long period of time.
April Fool's is always a fun time for astronomy. We have a lot of huge nerds in our field who have a lot of free time and write amazing, scientifically sound fake papers about Game of Thrones planets, or about weather impact on observing, or how to make your own acronym, and actually wrote the code to make an acronym for you. It's things.
There's incredible follow through on the ideas.
It is. They take it all the way to the nines. All right, I think we're probably going to call it. I don't see any more questions coming in, and I want to give another thanks to all of our amazing speakers tonight. Our undergrads do amazing science, and it is a huge honor to have them on our show and to showcase you guys and all of the things that you're doing. Thank you again, everyone. Great job. You're amazing, and keep it up.
I also want to say like a huge congrats to Isaac for graduating, and to Zoe and Dustin for making it through a very strange semester.
Yes, you guys have done a great job. This is a little bit strange, but I hope that being on Astronomy virtually still has the same kind of feel to being on our stage. Thanks again to Danny and Jackie for amazing news all of the time. And for, I'm not quite sure, I think Christine was counting pop culture references. I'm not sure how many we got up to, but we'll have to tally those up later. Thanks again for everyone who's watching. I really appreciate you tuning in. Please follow us on social media. Fill out the survey. A link is in the description of the video. Let us know what more you would like to see from us. And we will see you next month for geophysics and space. Thanks, everyone.
Bye, everybody.